All right, so so the second speaker of this second part of our session is Markus Lange from CISA, and he will tell us about Trotter product formula for star automorphisms of quantum lattice systems.
Yeah, hello. And I want to thank the organizers for the opportunity to talk about this joint work with Sven Bachmann, which is also available on the archive. And due to time constraints, I will not go into much details, but I want to convince you that such product formulas for quantum lattice systems are actually, that they are there and we can work with them, and they are well defined in the infinite volume limit, as we will see. But first, let's talk about the product formula. So such a product formula was proved by Sophos Lee in the late 19th century. And what he proved is that the exponential of any two matrices can, in a way, be approximated by a corresponding product of the exponential of the first matrix and the exponential of the other matrix, and then you need to take the corresponding limit of n going to infinity. And later on, in 1959, Trotter proved such a product formula in the context of semigroups on Banach spaces. Then also Kato came and proved this more in the context of quantum mechanics, especially in the context of path integrals. And there are many, many more contributions there, which I will not go into details. But lately, these kind of product formulas came up again in the context of, on the one hand, quantum information theory, and on the other hand, of condensed matter theory. In quantum information theory, such operator products are known as quantum circuits, and such formulas are interpreted as simulation algorithms for the evolution of the quantum system. And in condensed matter theory, such operator products are known as finite depth quantum circuits, and they have to do with gapped phases of matter. I will not go into that direction today. But what we obviously need is some kind of way of having this on a quantum lattice system in the infinite volume limit. So just think about a one-dimensional Heisenberg spin chain with nearest neighbor interactions, and then we can somehow split this up into a part, which in a way I call A here, which are somehow all the spins sitting on even lattice points interacting with their right neighbor, and then the corresponding odd parts where the odd integers spins sitting on integer points acting with their right neighbor. So in quantum information theory, you normally see some picture like this, where now in a way the dynamics generated by the even integers nearest neighbor interactions are depicted here in orange or yellow maybe, I don't know how it's displayed there, and the odd ones in red. And so what you're interested in is somehow how many of these layers of, in a way, quantum gates you need to approximate your full Hamiltonian via these quantum gates. So what we need is, in a way, a convergence rate for n going to infinity of these formulas. So if we just somehow naively compare these formulas in a way on n short intervals of the length 1 over n, then one easily sees that if we look at this, the zeroth order and the first order will vanish, and the first non-zero order will be of second order, and then we get this commutator here. And as you can see, we have the commutator of A and B, and obviously, as you see in this picture, and if you could see here also, they will not commute. So we will get some non-zero term here. But if we now naively somehow approximate this in norm, then you also see that we will get terms that have a norm of A and a norm of B in them. And if we would scale this to the infinite volume limit, we get problems there. So we need to be a bit more clever. But somehow, as in a way, as we have already seen in Amanda's talk, we have the way of writing this as local observables and as interactions, and with this notation we can then actually get more information out of it and actually solve this. So let me quickly define the objects I will need. You have already seen them in a way in other talks already, but we have some graph. Just think about Z as in the picture before. We have on each lattice side X a Hilbert space, so for spins, just think about C2. And then the local observables are defined for any finite subset lambda of this graph as the corresponding operators on the tensor product of these single-side Hilbert spaces. The algebra of quasi-local observables is then just the union of all the local observables completed within the norm topology. Let me mention here that we don't have a infinite volume Hilbert space we can work with, but we have this algebra of local observables on which we can work. And for locality, we have some of this defined as usual. So if we have a local observable A, which is supported on X, and we have a local observable B, which is supported on Y, then these two observables will commute if the corresponding supports not intersect. And with this, we can also define interactions, which are just self-adjoint self-adjoint maps on from the finite subsets of gamma into the local observables. And we can define finite volume Hamiltonians as somehow sums of these interactions. So this is the basic notion, and then we can also define what the dynamics is, where this is just a strongly continuous group of star automorphisms on this quasi-local algebra, and it's given by the limit of lambda going to gamma of the usual finite volume dynamics. This dynamics is well defined, and this limit exists due to the Lieb-Robinson bound, and somehow if the corresponding interaction phi is sufficiently local, I will come to that later. But also I want to define the generator or the star derivation of this dynamics, which is for, as you can see here, you can actually use the mouse, right? Which you can see here is for local observables, or strictly local observables, which are supported on some set Z, just given as this limit here. So you get a limit again of lambda going to gamma, and then we have this commutator here of the Hamiltonian and of the observable O. Again, this limit is also well defined and exists for sufficiently local interaction phi. And now I can actually say what I mean with local interaction or sufficiently local. That means that it somehow decays fast enough in the diameter of the set X on which it is supported, or on these sets X. So what you see here, in a way, we have this generator or star derivation, which is well defined, and we have this dynamics. So we can actually go to the infinite volume limit and consider such product formulas. Now, if you think back on the first slide, we saw that somewhat naively, we split up everything into n short time intervals and compared them on the length 1 over n. If we would do this here, and in a way we would then use something like Duhamel formula, we would need to consider, first of all, generator or star derivations of strictly local operators, but then also in higher orders, star derivations of local operators, and so on and so forth. But as you see here, we have this commutator, so this will actually not be strictly local anymore, so we might get, and we will actually get, some problems there. So we need to fix that. But this is, in a way, easy to fix, because we can treat all observables just as interactions. And then on the set of interactions, our derivation is actually a bounded operator. And it's just rewritten it here, we interpret it as now acting on the interactions. And then if we start with a strictly local observable, then this is actually almost localized. I will just say almost localized means, in a way, that we have it not only localized in the diameter of X, as you've seen in the last slide, maybe we can go back here, but it's also localized in the distance it has to the support set of the Z of the observable O. So we are not only localizing in the size of the sets X we consider, but also in the distance to the corresponding support of the observable. And this, in a way, means almost localized. And what we now somehow can see is that these star derivations are actually, these almost local observables are in the domain of this star derivations. So if we start with an almost localized observable, then we end up in an almost local observable we get out. And this is actually bounded, the interaction norm of this now interaction of the star derivation is somehow finite and bounded. So this is fine. And luckily, the Lieb-Robinson bound again comes in, and we can get the same for the corresponding dynamics, which is generated by the star derivation. And we also get there that we can bound the interaction norm of this dynamics by the corresponding interaction norm of the observable and some constants. But what we see here, these constants, or actually you don't see it, but if I would go through the proofs, these constants do not depend on the size of the system we are looking at. So we actually have now a bound that does not grow with the system size, but somehow is in a way localized. And what this morally means is that we can do this Duhamel expansion and actually compare the corresponding dynamics of the full system by the corresponding product automorphism we will have. And let me come to the result in a way. So first of all, what do I mean with full system and somehow product system? Let's just say we have some interaction phi, which is a sum of interactions phi j. As I maybe show this picture again, so you can just think about the case where you have k equal to 2. There we have some of these interaction phi 1, which corresponds to this dynamic tau 1, and the interaction phi 2, which corresponds somewhat to this tau 2. And we have these layers, and what we're interested in, if we have a way to approximate the full dynamics generated by, or given by this interaction phi by these interactions phi 1 and phi 2, but some k can be arbitrary. And I will call an arbitrary decomposition, arbitrary composition of these dynamics given by this tau phi j as a product automorphism. So in a way, these blocks here are the product automorphism in this case. And what Sven Bachmann and I then showed was that if we fix some natural number m, then there exists a product automorphism, which I call pi m, and then you have the time and n of this quasi-local algebra, such that we can approximate the dynamics generated by the phi by this product automorphism with an error that somehow behaves like 1 over n to the n. So we can really scale, we can really say what kind of decay convergence rate we have there. This is again written here for strictly local observables, but we can actually do it for almost local observables because some of this generator and also the dynamics are again well defined there, and we have this bounded. And I should also mention that the number of factors in this this product automorphism are of the order n, but that is somewhat to be expected because we want to get such a product formula as I showed on the first slide, where you also get a number of factors of the order n. And then, maybe as the last thing, I don't know how much time I have left, I just want to mention that this constant Cm, which I don't really give you here concretely, really depends horrendously on m. So you should not try to optimize this in m in a way. You should fix m, and then you get this rate for n going to infinity. But again, this is expected because we use here some symmetrized higher order formulas, which were proposed by Suzuki in 1991. And so you have a huge number of terms which come into this. But for any fixed m, you can let n go to infinity, and you have this nice rate of convergence, and you have this product automorphism in the infinite volume limit. So let me finish. I hope I convinced you that there is a Trotter product formula in the infinite volume limit and that it is somewhat useful. And I also hope I convinced you in a way that you can generalize this to higher orders in n so that we get arbitrary fast convergence. And if you're interested in more, look at the archive paper or ask me and I can answer this. Thank you for your attention.
Thank you very much, Markus, for the nice presentation. Is there any question? So I think I have one. So I mean, how explicit is this pi m at the end? I guess it's constructive what you do.
Yeah, the pi m is actually very explicit.
Right.
So for a given m, and some also, it depends also on the k here, we get a very explicit formula how it needs to look like. It's in a way just a symmetrized formula where you, the details are in the paper. I cannot really write it down.
Okay. So if, like, am I wrong if I say like if m is 1, this would just be the naive Trotter thing, like the product of, okay.
In a way. So for n equal to 1, m equal to 1, you get the naive Trotter thing. If you want to do m equal to 2, you would somehow use, so the exponential would be e to the, let's say, a half, e to the b, e to the a half,
sure, yeah.
and then you would somehow construct further on.
Yeah.
But there's an explicit formula how you have to choose it. And you actually, that's actually interesting. You actually get that you don't always somehow propagate forward in time. You actually have terms where you go backward in time, and there it comes back with these path integrals. You actually get a fractal path somehow of the of how you evolve in a way, because you have somehow. But you need to do this because you have some cancellations there which you can use, and then you get this. But it's more complicated.
Okay. Thank you very much. Other questions? Online, if anyone has a question online, please unmute yourself. Probably.
The speaker online.
Okay. So, well, let's thank Markus again then. Let's move. Okay. Hi, Robert. Can you hear us?
Yes, I can. Can you hear me too?
We can hear you. We can see you. Yes. Good.
Perfect. Yeah, now you should also see my slides, I hope.
Perfect.
Perfect, great.
Okay, so the last speaker of today's session is Robert Salzmann, and he will tell us about quantum Zeno effect in open quantum systems. Please, Robert.
Yeah. So thanks a lot for the introduction. As you've just heard, my talk will be about the quantum Zeno effect in open quantum systems. It's based on a joint work with Simon Becker and Elanjana Datta, and if you want more information, please consider the paper we recently published. So let me give a very brief introduction. So, I mean, the quantum Zeno effect is probably known to many of you, and it roughly tells you that if you frequently measure a quantum system, this slows down its time evolution and eventually freezes it completely. And okay, it has been shown it has shown that there are many applications. So, for example, in quantum error corrections, control of decoherence, state preparation, just to name a few. And okay, what I want to discuss today is like generalizations of quantum Zeno results for open quantum systems. In particular, we are interested in generalizing the infinite dimensional cases. So, okay, what is the setup of the quantum Zeno effect? There are basically two ingredients. One is some time evolution. So, okay, consider us in some open quantum system, and the time evolution is now governed by some Limblad equation, as you can see here, where this L is the Limbladian of the system or the generator. And as we all know, the solution of this is given by some dynamic semigroup, okay, and which consists of like completely positive trace preserving maps. And okay, this is a solution, and here you have a pictorial representation of it. So the second ingredient of the Zeno setup is in our case, some quantum operation. So for me, this is a completely positive trace non-increasing map. And okay, you can think of this being just some quantum channel, but you can also think of applying some measurement, and then this could be some operator within some generalized measurement collection, let's say. So then the full setup is you have this state and you let it evolve for some time t over n with your semigroup, but then you apply your quantum operation and you do this whole process n times. So you frequently interleave your dynamics with this quantum operation. And then a natural question, of course, to ask is what happens to this process if you consider the infinite application frequency limit, right? So this is the process, again, pictorially, and it's represented, of course, by this product formula, the Zeno product. And okay, what happens to the Zeno product for if you send n to infinity? So let me recall some known results from the literature. So if you consider the special case of M being a projector and a bounded generator, then Matolsky and Schwidkow proved in 2003 that the Zeno product converges in uniform operator topology to this effective dynamics, which is generated by an effective generator PLP, and it basically just restricts on the Zeno subspace given by the projector P. And then there was this very recent generalization where you now really consider a bit wider class of quantum operations. So Möbius and Wolf extended to quantum operation which satisfies certain spectral gap or certain spectral condition. And I will talk about this in a minute. And what they found is also the conversion of the Zeno product in uniform operator topology towards this effective dynamics, where now the P is the projector on invariant subspace of M. Okay. So now I want to go to what we can show currently. So we provided a quantitative version of Möbius and Wolf's result under some generalized spectral condition. Then we were also interested in understanding the spectral condition a bit better, and we found that it's actually necessary for uniform convergence of the Zeno product. And then using this quantitative bound on the speed of convergence, we were able to extend to unbounded generators. But all of these results are under the spectral condition. So we found that actually many models from quantum optics fortunately do not satisfy the spectral condition. So we were very motivated for trying to find a Zeno result without this. And okay, so this is what we've done. We found some Zeno limit result which then holds in strong operator topology while omitting the spectral condition. First I want to talk about the spectral condition on M, and as I've mentioned, this is connected to uniform convergence of the Zeno product. So the spectrum of this quantum operation is defined in the sense as we all know it, some subset of the complex plane, and the spectral condition now consists out of 2 points. So first, because the quantum operation is a contraction, it has norms smaller or equal to 1, it's clear that its spectrum is contained in a unit ball, but we assume something slightly stronger, which is some spectral gap. So we say, we only allow one spectral point on a unit circle, which is 1 here, and the rest of the spectrum is contained in a ball strictly smaller than 1, as you can see here. And let me emphasize that actually, even though I don't want to go into the details in this talk, what we can do is having arbitrary but finitely many isolated points on the unit circle, and we get a very similar result. So the second part of the spectral condition is left open, so let me try to interlude to this. So because we have the spectral gap, what we can do is we can find some closed curve gamma which separates this point 1 from the rest of the spectrum, and by that we can define the spectral projector associated to the spectral point 1 using this holomorphic functional calculus, as you can see here. And if you think about finite dimensions, then this projector would really be just a projector on the corresponding Jordan block. So then associated to this projector, you can define a quasi-nipotent operator, which basically just looks whether your operator M on this projective subspace is given by the identity or not. So this is, as I said, quasi-nipotent. It has spectrum equal to 0. And what we just assume in the spectral condition is that this quasi-nipotent operator is 0. So there, it's trivial. So this is the spectral condition. Let me try to now connect it to convergence of these product formulas. So what we can show is that this spectral condition is actually equivalent to convergence of kind of the trivial Zeno product, right? So if you take the generator L equal to 0, this is what happens to the Zeno product. And the spectral condition is equivalent to convergence of this in uniform operator topology. And this, of course, then tells you that the spectral condition is necessary for uniform convergence of Zeno products. But actually, we get something slightly stronger. So these two statements are equivalent to exponential convergence of these powers. So you have some exponential decay rate of this convergence. Okay. So just to fill it up with some example of some interesting channel which satisfies the spectral gap, let me consider this generalized depolarizing channel. So you have some fixed state sigma and you have some probability p, and what this channel does is it mixes. So with probability 1 minus p, it acts as the identity channel, and with probability p, it acts as the replacer channel, as you can see here. And can then show that this actually satisfies the spectral condition. So, okay, the spectrum has obviously some spectral gap. You can also show that this quasi-nilpotent operator is 0, and the projector on invariant subspace is then just given by this replacer channel. So this is some quantum operation, or actually quantum channel, which satisfy the spectral gap and for which the now following results would apply. So yes, I now want to go to really the non-trivial Zeno products, so it's non-trivial generators L. And first, I would like to consider the case of L being bounded, so bound generator, and okay, M having the spectral condition I just mentioned. And what we then find is that the Zeno product converges uniformly to this effective Zeno dynamics, and we have this bound on the speed of convergence. So for n to infinity, this obviously goes to 0. And as I stressed earlier, we can actually get a very similar result when we allow for finitely many isolated spectral points on the unit circle, but I omitted this here for simplicity. And to give you some intuition how you would go and try to prove this result. So here's the idea of the proof. It really heavily relies on having the spectral gap, basically, that you can isolate the spectral point 1 from the rest. And you do this by using these holomorphic functional calculus tricks I've showed you earlier. And as soon as you've done that, you can basically apply techniques for the special case of M being a projector. And okay, these techniques can be like, for example, this Chernoff square root lemma, which maybe some of you might have heard of. So okay, this is some result for bound generators with a quantitative bound on the speed of convergence, and we now can use this bound on the speed of convergence to extend to certain unbounded generators. So this is the result. We have some unbounded generator of some strongly continuous semigroup, some quantum operation which again satisfies the spectral condition, and we also need some uniform boundedness assumption. So we say that the operators ML and LM are both densely defined and bounded. And what we then get is convergence of the Zeno product in strong operator topology. So pointwise for all states in trace norm, as you can see here. And okay, I've mentioned already that the key to prove this is the quantitative version of the result for bounded generators. So okay, what you do in order to prove this theorem is you consider bounded approximations. So in particular, we had these Yosida approximants. So they're defined by these resolvents. They're, as I said, bounded and approximate the generator on its domain. And if you now plug those into the quantitative result for bounded generators and consider a coupled limit k and n to infinity, you basically get this result. So this is how these two results relate to each other. Okay, so now I want to go beyond the spectral condition. So basically everything I've talked about so far, and also everything which is known so far in the literature, let's say, is you assume the spectral condition on this operator M. But unfortunately, we found that many interesting models, for example, from quantum optics, do not satisfy the spectral condition, and therefore we wanted to extend the results to the regime without a spectral condition. So let me give a motivating example of a channel which does not satisfy the spectral condition. So let me take this attenuator channel. So this comes with some parameter lambda, which is strictly smaller than 1, and then you can define it easily on coherent states, because if you plug in a coherent state, it gives you a new coherent state with this damped parameter out. And from there, it's not hard to see that if you take your M to be this attenuator channel with some fixed lambda, then this converges strongly to the projector on invariant subspace, right? So for all states fixed. However, this does not hold uniformly. So if you consider this difference in norm, okay, this is just how it is defined, then you could define, can you lower bound the supremum by the supremum over all coherent states. And now we know how both of these operators act on coherent states. So this is what you get. And of course, if you fix some alpha, this goes to 0 for n to infinity because lambda is strictly smaller than 1. However, if you first consider the supremum over all alpha, this will be just constant 2. So what this tells you is that these powers do not converge in uniform operator topology. And therefore, because like uniform convergence is equivalent to the spectral condition, the attenuator channel does not satisfy the spectral condition. Okay. So therefore, none of the results apply. This is a bit sad, but there's a little hope because we have this power convergence, the strong power convergence assumption. So this is something which the attenuator channel satisfies. So, okay, the question is, can we actually extend Zeno product convergence under such a strong power convergence assumption? And the answer is yes. So this is the last result I want to talk about. So it again only holds for bound generators, and we have some M which not necessarily satisfies the spectral condition, but the strong power convergence assumption, just as the attenuator channel. And then you get again strong convergence of the Zeno product towards the effective Zeno dynamics. And just to compare to the proof methods I've shown you earlier, let me give some idea of the proof. So I've said when you have the spectral condition, kind of the key is you to separate different spectral parts of M, and you use holomorphic functional calculus techniques, right? And of course, this is not possible here because you might not have the spectral gap, or you know nothing about the spectrum basically. So what you can do is you can read the semigroup as some perturbation of the identity plus some order 1/n term, where this Ln converges basically to your generator. And if you plug this into the Zeno product, this gives you a perturbation series expansion of the Zeno product in different powers of 1/n. And then you can collect all of them and control each of them individually. And what you will then see after some technical issues is basically this effective dynamics again. Okay, so let me come to an end and quickly summarize what I've talked about. So we have now this quantum Zeno limit for bound generators with the spectral condition and provide some bound on the speed of convergence. And we can use this to extend to unbound generators, but under this uniform boundedness assumption. And we also need the spectral condition on M. And moreover, we were then able to prove some Zeno limit without the spectral gap, which, for example, applies for this attenuator channel. And just to state some open problem, of course, it would be very interesting to extend the result for unbounded generators. So it would be very desirable to replace the uniform boundedness assumption by some pointwise boundedness assumption, which depends on the state which you put in. So, for example, some energy constraint or so. And the question is, can you do it with or without the spectral condition? So, because currently we don't have any Zeno limit result for unbounded generators without the spectral gap. So, yeah, this is the end of my talk. Thanks a lot for your attention.
Can you hear me, Robert?
Yes.
Okay, good. Yeah, okay. Thank you very much for the nice presentation. Is there any question on site? So I think I have one, but perhaps you maybe that's related to what you were mentioning in the conclusion. So I mean, if instead of looking at this norm convergence, you would look at the convergence of certain classes of averages of certain class of observables, do you think it would be possible to get a bound which doesn't depend on the norm of L?
Sorry, I'm not sure whether I understand. So what do you want to average over?
Your estimates depend for the bounded case, in which L, for the bounded case, depend on the on the norm of L, right?
Yes.
But then, I mean, if you would consider, let's say, instead of a norm convergence, let's say convergence in the sense of averages of certain observables, would it be conceivable?
So in some basically weak convergence.
Right. Yes. Would it be conceivable to get error estimates that do not depend on the norm of L?
Yeah, that's a good question. I mean, okay, probably like the farthest, like the best I know is this strong result, right? Where you also don't have the norm appearing, but basically this is completely non-quantitative, so I don't know any bound on the speed of convergence. Interesting question. I mean, I don't know. Maybe it's possible. I don't know.
Okay, thank you. So we have another question, which is, do you know what happens for sectorial operators? The question received online.
So sectorial operators. I mean, I think there are some results for like in the Hilbert space case, but I also don't recall them. So unfortunately, I can't provide a good answer to that. Sorry.
Okay, other questions? Okay, so it doesn't seem to be the case. So thank you very much again.
Thanks.
And thanks to all the speakers of today's session.